So far we've looked at the causes of noise, we've looked at the effect of noise on amplifiers, and we finished up with the last lecture looking at a concept called shot noise, which is a function of the amount of current that are flowing through through a junction device such as an FET or a bipolar transistor. In this third part of this lecture, we're going to look at a final type of noise called flicker or 1/f noise and how it impacts amplifier performance. So in a normal piece of wire or an ordinary piece of circuit, the current flow happens fairly linearly, and in this model here is moving from left to right. And the noise associated with that current is actually quite constant. However, in real devices, we often have defects where the charge is not uniformly distributed throughout the junction, and it can actually have small random perturbations in the amount of dopant within a given junction. And these defect charges trap and then release the currents as it's flowing through. So the current is flowing through the device, and a defect traps an electron, and then another electron bumps into the defect and the first electron gets knocked out. So you land up with these variations, minute variations in current, which is called flicker or 1/f noise. The effect of this is we get sharp increases and decreases in current. So here we've got the current flowing through the junction, and we've got high current. We have a noise trap here at this point here. It is then released back into the current flow. The current increases again, then some more traps happen, and we land up with discrete changes in the noise due to this concept called flicker noise. And it's really all fundamentally down to the quality of processing, how you actually manufacture your transistors. Or the reason it's called flicker noise is that it flickers on and off randomly, very like a candle or perhaps a broken light bulb, and has an approximate 1/f frequency dependent. You can think of it almost as a random frequency square wave. So if we plot here the log of current noise in amps per root hertz, as we increase in frequency, the flicker noise decreases, and it would continue decreasing, except in real amplifiers it would cross the point of the thermal noise, form the amplifier, and that would then take over as the dominant noise source in the amplifier. At this point here we have a corner frequency, and that identifies the changeover between 1/f or flicker noise and also the thermal noise. Flicker noise can vary between devices and can even vary between devices of the same type and same manufacturer. And we've shown it here as a noise current, a flicker noise current, but equally we can also get flicker noise voltages occurring within amplifiers. But they can be generally lumped together as 1/f noise. Looking at some real devices, and this is a very common op-amp, a TL071. What we have here is the frequency along the bottom. We see that the noise drops with frequency. The noise current for this amplifier is defined as 10 femtoamps. We've got a bias current of 65 picoamps. So we can actually work out the shot noise from this circuit here, and we land up with a shot noise of about 4.6 or 5 femtoamps per root hertz. We can also work out the best noise source matching, because we know what the noise voltage is. It's 18 nanovolts per root hertz. We know what the noise current is, and dividing those through we can get an ideal match from a source resistance standpoint of 1.8 megohms. If we look at the curve here, we can actually draw on the graph two simple lines. One is the thermal noise or the flat noise, which is approximately 18 nanovolts per root hertz, and the second one here is an approximation to the 1 upon F noise, and we find that it crosses at a point here of about 200 hertz. In other words, this TL071 has a noise corner frequency of around 200 hertz. We can now look at some other devices. On the left here we've got an NE5534, a very low cost, a cheap bipolar amplifier, and although the graph here actually doesn't really show how steep the curves are increasing, we can actually do some calculations and work out the corner frequency here is about 60 hertz. And a rule of thumb figure for corner frequency is if you take the steady state frequency here and approximately double it, it gives you a good indication of what the noise corner frequency looks like. If we now look at a very high quality op-amp, an OPA 827, we have a nice noise voltage of 4 nanovolts per root hertz, which is comparable with the NE5534, the cheap and nasty bipolar amplifier, but here we have a lot lower noise current than this one here, and it means that we have an ideal match resistance of about 1.8 megohms, very similar to the TL071, and we can actually work out our, since we've got a bias current here, we can work out a shot noise due to the bias current of about 1.8 femtoamps per root hertz. And looking at the overall impact here, we can work out that the overall performance of this amplifier has got a 1 upon F frequency of about 20 hertz, which is an excellent number and very low noise indeed. Looking at even more devices, here we have a typical low noise OPA 177. This is an MOS amplifier, and looking at the noise from the graph here, it's important to note that the bias current in this amplifier is compensated for. So we land up with excess noise, shot noise, due to the bias current compensation. And the real bias current that we would have if we did not have bias compensation here would be about 125 nanoamps. So you can see that the bias current has reduced dramatically by using the bias currents compensation circuit, but underneath, the noise due to that unbiased circuit is still prevalent. And we land up with a noise frequency of about 15 hertz for this amplifier. A low noise bipolar instrumentation amplifier, a specialist one, we land up with a noise current frequency of about 10 hertz here. And the perfect match here is 667 ohms, which would be ideal for matching for things like a load bridge, a load detector, where it has 4 resistors of perhaps 600 ohms each. So summarizing for our noise, in the case of thermal noise increases with temperature, but it is uniform over frequency, and the power spectral density of thermal noise is present in all resistors. Whereas in the shot noise, it increases with current, it is uniform with frequency, and is only present in some sort of devices, particularly devices with junctions, where the current flow has to cross a potential barrier, and it happens in random events. And the final type of noise here is 1 upon F noise, or flicker noise. Flicker noise increases with current, but is only present in some device types. And in particular, the flicker noise increases at low frequencies with a 1 upon F relationship. So when you're designing your amplifiers and when you're designing your systems, you need to consider what the source resistance and the type of signal you're receiving from the detector or the sensor, and design and choose your amplifiers accordingly, trying to match the amplifier performance and the amplifier noise performance in particular with the individual sensor or detector that you're using. In general terms, you should always try to limit the bandwidth, because in all these noise types, if you reduce the bandwidth, you reduce the overall effect of noise. And the last point is, if you can keep to low value source impedances and resistances, that will be beneficial to your design, because we will not be adding excess noise. Thank you very much for listening to that, and we've now looked at all the noise sources as applied to amplifiers. In the next lecture, we will look at doing some further noise analysis, which will then complete this course on electronic system design. Thank you very much.